Okay, so the goal right here is we want to approximate the area under a curve. So for now, for today's lecture, you should forget everything we've learned so far, right? Today's lecture is kind of separate from everything else, except limits, but everything with derivatives is completely irrelevant for now. We'll come back to derivatives next lecture. Okay, so we want to approximate the area under the graph of y equals f of x and above the interval AB on the x-axis. So for technical reasons, first we'll assume, for now we're going to assume that the function is continuous and positive, or not negative. So we assume f is continuous and non-negative. We'll talk about later what do we do if the function is either not continuous or not negative, or have some negative values. We'll talk about that later. So let's draw our function here. And let's see. So there's our function. And I want to get the following area. So here's A, here's B. So what's the area that I want to get? I want to get the area of this shaded region. How are you going to do that? How would you estimate that area? What do you think? What do you think we should do? It's a good question. How would you estimate this area? Count the blocks. In second grade, Caleb, we count these little blocks. Do 1, 2, 3. Do you think that's a good idea, Dashika? Counting all those blocks and estimating? You don't think that's a good idea? What do you think is a better idea? Hirsch, would you divide it a Riemann sum? What the hell is a Riemann sum?
No, like, would you divide into like x1, x2, and so on?
What is that?
I thought that was just the best thing you had to do.
Break the interval to small pieces? Well, that's going to be one of the things we do. In fact, actually, Caleb's idea is actually very good. In fact, that is actually what we do. We count the blocks underneath this thing. I don't know why you all thought it was a bad idea. I mean, I think it's a great idea. So we count the blocks underneath, right? And these partial blocks, we might say, okay, let's just say that's like a half a block or something. Now, obviously, we're going to sit there and count boxes. We are going to have a better way of doing it, but that's basically what we're doing. We're basically counting the boxes under this graph. But we're going to do it in a more systematic way. So let's see. Can I search for my old graph? We're going to do it like this. So that's what happens. Now, so we divide the interval up into several pieces. So first, basically what we're going to do is we're going to use rectangles underneath this graph to determine what the approximate area is. Maybe we can make this a little bit smaller. Move it over. Okay. So there's a few steps to this. So first, notice that I've taken the interval AB and I've divided it up into several x values, right? So you divide the interval up into several equispaced pieces, right? All of the bases of the rectangles are going to be the same, right? I have, well, in the picture, I have 6 rectangles. They all have congruent bases. That's the idea. You split up the interval into however many rectangles you want to use. I'm going to use 6 rectangles. Okay, so let's write that down. So 1, use rectangles whose bases lie on the x-axis to estimate the area. Okay, and how do we get those bases? We divide up the interval into equal pieces. All right, so divide the interval AB into n. And again, n is the number of rectangles. It can really be any number you want. Right now I'm choosing 6. So divide the interval into n equal length subintervals. Okay. So these subintervals are the bases of the rectangles. Now the next thing. I have to talk about how do you determine the height of the rectangle, okay? So again, these pink rectangles that I've drawn, I just want to make clear, they are meant to approximate the shaded area underneath this graph. And ultimately what we're going to do is we're just going to calculate the area of these rectangles, doing length times, width times height for each rectangle and adding up all the areas. And that's going to be our approximation of the shaded area. It's not exact, but it's an approximation. So it's basically what Caleb said, we count boxes. Except we've actually done it a little bit different. Since we're using rectangles, sometimes we get extra boxes, sometimes we don't get as many boxes as we need, right? So sometimes there's an overestimate, sometimes there's an underestimate. But one question we haven't answered yet is, how do you choose the height of the rectangle? For instance, once you have the base for that first rectangle, I mean, what's stopping you from making a rectangle that's like that? I mean, I wouldn't make a rectangle like that. That doesn't seem like a very good approximation. But what rule am I actually using to calculate the heights of these rectangles? Because there are many ways I can. So generally speaking, there really is no rule to the rectangles, but you decide on a rule before this. So the rule that I'm using, or actually first let me say, the rule that you should always use is the height of the rectangle should intersect the graph. So for instance, let's look at the first subinterval. So this blue base. So this blue rectangle, where should you put the height? The height should intersect the graph. So the height should intersect this piece of the graph. So I can make the height, say, here, or here, or here. Anywhere along this graph, I can say, okay, there's the height, I'm cutting it off, and then that's my rectangle. That's generally the rule we keep to. Okay. Now it looks like Thomas has figured out the actual rule that I used in my picture, and he's right. So the rule that I use is I will always make the height intersect the graph at the right end point. So here's my graph again. Let me highlight it. Here's my piece of graph. I'm choosing my height so that it always intersects at the rightmost point. And there's my height. If you look at any other piece of graph, so for instance, let's look at the third rectangle. Here's the piece of graph that's above the third rectangle. I'm choosing the rightmost point, and that's my height. So these are called right endpoint rectangles. I mean, right, what else would you call them? You can choose left endpoint rectangles, you can choose midpoints, you can choose kind of just a random point in between, right? As long as the top of the rectangle intersects the graph, you're all good. That's our only requirement. So choose height of rectangle. So top intersects graph. We will choose the height of each rectangle to be the function value at the right endpoint. mean, all these notes are in the lecture notes if you don't want to. All these words are in the lecture notes if you don't want to copy down every single thing. Function value at the right endpoints of each subinterval. And then the last step, as I alluded to, is, okay, now that you've drawn your rectangles, calculate the area of each rectangle, you know, width times height. They're all the same width, which is nice. And add up all the areas, and that's the area. That's the approximation of the area underneath their graph. That's it. So total area of rectangles estimates area under the graph. That's it. Okay, so one little piece of notation. So if we use n rectangles with right endpoint heights total area of rectangles we denote by Rn, call it Rn, right endpoint, n rectangles. And call it, Hirsch, what do we call this?
We call it a Riemann sum.
A Riemann sum. So it's named after the mathematician from the 1800s, Georg Bernhard Riemann, father of modern geometry. He's got a wicked beard if you look him up. He's got one of these like wizard beards. Okay, so now let's talk about this conceptually. So Nishika, do you think these pink rectangles, that's actually a good approximation? Do you think we're going to get a pretty good estimate of the area under the graph?
You could get a better estimate by putting more rectangles.
That was going to be the next question. How can you get a better estimate? You can just use more rectangles. So I already have a picture of this, hopefully. I'll have to redo it. Yes. So let's see. So what happens? So what happens if I had 8 rectangles and then I doubled it? So let's look at this. So you might not be able to see it too well, but I originally had, let's see, I'm going to highlight it in orange temporarily just so you could see it. I originally wrote here, or drew here, I think 8 rectangles, right? I'm highlighting them in orange. So originally I had 8 orange rectangles. And then what I did was I divided each of those 8 rectangles into 2 rectangles that I ended up with 16. And I ended up with these 16 purple rectangles. Those are kind of outlined. And so what has happened, right? I mean, this should be pretty obvious. What happens if I increase the number of rectangles? In general, you do get a better estimate of the area under the graph. So if we increase n, we seem to get a better approximation. A better estimate of the area under the graph. And how would you get an even better estimate? Well, you can divide each of these purple rectangles into 2 more rectangles. And now I'll have 32 rectangles, or however many I would have. And I can get an even better estimate. Now, what process does this remind you of? This is a central construct in calculus. What does this remind you of? I just wrote a statement. If I increase n, I get a better estimate of the area under the graph. So as n gets larger, the area under the areas of the rectangles gets closer to the area under the graph. What am I describing to you? I'm describing a limit, right? So in fact, that is actually how we define the area under a graph. This is actually an interesting question. No one actually asked this because it's kind of subtle. When I actually, at the beginning of the lecture, I said, we're going to talk about the area underneath this graph. No one even batted an eye that this area didn't even possibly not exist or be undefined or not well defined. I mean, here's a good question for you to think about. How would you define the area underneath this curve, right? This, the shaded area. How would you define the area under the curve? In fact, this is how we define the area under the curve. We actually define the area under a curve as the limit that you get from approximating it with rectangles. So in calculus, we actually assume from the start that we don't know how to find the area of anything. We just declare by fiat that the area of a rectangle is length times width. And then we use that to approximate all other areas. In fact, that's how we define all other areas. So a priori, the area underneath this graph didn't really exist or make sense until I just defined it for you. The exact area underneath the graph is actually defined to be the limit as n goes to infinity of Rn, right? You take the limit of the rectangles as n goes to infinity. So it's kind of an interesting thing to think about, right? That the area actually doesn't even make sense until I make this definition. Okay. So that's how we define areas. And that's where limits come into play. So now let's get some special notation. So if you want to figure out the area of a circle or the area of an ellipse or something like that, it comes from this definition. So like I said, we define the exact area under the graph and above the interval. Right, I have to write all this out to make sure that we're very precise with our answers. So the limit of the associated Riemann sums as n goes to infinity. Okay, and now our special notation. So we denote this with a very special symbol. It's the integral symbol. So this exact area is denoted so we use this integral sign again. So we say it's the integral of f of x from a to b. So that's how we denote it. So notice how this nice compact notation actually tells you everything, right? It tells you the interval on the x-axis, right? It gives you a and b. It gives you the function f of x. It also tells you the variable, right? Otherwise, we'd assume all other variables are constants. Now, I know a lot of you have seen calculus, so this doesn't seem as magical to you, but let me kind of try to disabuse you of that, especially, so if the students who have never seen calculus before, this is actually great because you have not been tainted by what other high school teachers have told you. So you may have noticed that when we did antiderivatives, when we did initial value problems, we used the same symbol to denote antiderivatives, right? I said that this thing, if I wanted the antiderivative of a function, I would denote it like this, but notice that there's no a and b. It's just with just the symbol, just the integral symbol. So the reason why we use the same symbol for antiderivatives and integrals is actually very important because it turns out that there is a link between them. It turns out that an integral can actually be computed using antiderivatives, which is not at all obvious. There's no reason to expect that areas under a graph have anything to do with derivatives, right? I mean, but we'll do that in the next lecture. So, Caleb, do you think that they should be related? Area under a graph and the slope of that graph?
No, I don't see how.
Yeah, it's not completely obvious. You might think maybe the slope of the graph kind of like tells you how much area you're sweeping out, but it's not completely obvious how that works, right? So, so this is actually called, your textbook will call this a definite integral. I just call it an integral because there's only one type of integral. And finally, another note. You should always be careful in mathematics when something is defined as a limit. Mohammed, if I write something as a limit, does that mean that thing is absolutely going to exist? All limits exist? Right, no. Right, so once you define something in terms of a limit, you open up the possibility that that thing might not exist in the first place. It actually turns out that this is true even for this. There are some functions for which this limit does not exist, and so the area underneath that graph does not exist. It makes no sense to talk about that. However, there's a very nice theorem in the book that actually guarantees that this limit always exists for certain functions. So note this integral, or I should say, so the integral, which is the limit of this thing. So the limit exists for all functions that are continuous on AB, except possibly at finitely many jump discontinuities. In fact, I can actually say a lot more, but this is what we're going to use in this class. So any function that is continuous, except possibly for some finitely many jump discontinuities, the integral always exists. So in other words, the integral, this limit actually exists for quite a large range of functions, very large category. So if something has a jump discontinuity, that's still fine. We can still figure out the area underneath the graph. There are some functions though that I can write down that don't have an integral, but we will not encounter them in this class. So in this class, there are functions we deal with that are